All right, this is Mr. Jern, and I'm going to talk today about AP Physics 1 Workbook 1B, Position and Velocity. So in this scenario, remember, always read the scenarios very carefully, even if they're short, especially if they're short. Angela is running at 3 meters per second toward the bus that is 15 meters away. So here she is again. We've seen her in Workbook 1A. She is running toward the bus. It's still 15 meters away, just like it was before. And part A says we're using representations. Now, using representations are a variant part of physics, AP Physics 1. Anybody can be trained to plug numbers into a formula and what we call plug and chug. You put numbers in and you get an answer. And that doesn't necessarily mean you understand what's going on. Many students over the years have been able to get through physics and they come out the other end and they have no idea what just happened because they were able to follow directions. Teacher says, put a number in, this number, a D means displacements, plug in the numbers and boom, you got your answer. Okay, cool. But that doesn't mean you understood it. So an important part of physics is to be able to represent a situation in many different ways. The mathematics is one representation. But in essence, mathematics is still just writing. It's writing in a different language. It's writing in math. Here, we're going to start to use more pictorial or visual representations. So part A, which is important because it shows you can understand it, but it helps you understand it and it shows that you understand it if you're able to use these. So here we have a table below. Here, I'll read it, what it says. Below is a table of Angela's position at each second. Complete the table. Then, on the diagram of Angela and the bus, create a motion map of Angela's position at every second. Do this by marking with a dot where Angela is at every second. Okay, let's start with the table. It says she's moving 3 meters a second, 3 meters per second. That means for every second, Angela moves 3 meters. Okay, got that? If you say it out loud, 3 meters per second. Do that with everything and things start to make a little bit more sense. So if you have 0 seconds, she has moved 0 meters. 1 second means 1 meter and so on. So basically every second that goes by, she has moved 3 additional meters. All right, so her position increases by 3 every second. Then here is sort of the visual representation, the motion map. A motion map is typically just like this. It's a bunch of dots that represent where the object is at any given time. So we have our Angela starting at 0, 1, 2, 3, boom. So basically this is 0, 1, 2, 1, 2, and 3 meters, and so on and so forth. So basically, for every 3 meters we count off, we can add our little dot, and so we do. I actually think having the numbers down there is going to be helpful, so I think maybe you should add those, but that's what a motion map is. Now it's just asking for position, and that's kind of important because a position is just a place. It says you can use a dot. It says you should use a dot, but you might think of it as like an X. X marks the spot. Here's where Angela is at those times, right? Later on, we're going to make a motion map of Angela's velocity, but I don't want to get ahead of ourselves. But that's going to involve an arrow showing which, like her speed. Okay, but I am getting ahead of myself here. That'll be in another workbook page. Okay, so motion map. Now, those X's aren't actually necessary. The dot, it does say to put dots, so please don't add X's if it says to use dots. Okay, it specifically says with a dot. All right, so make sure you do that. Part B, another way to represent Angela's motion. See, there's multiple ways to represent motion, multiple ways to represent things with a mathematical equation, with a motion map, all sorts of things. In this case, it's what we call a graphical diagram, or a position versus time graph in this case. So finish filling out the data points, the data table above, and then mark Angela's position at every second on the graph. Plot the data points with a solid filled in dots. Okay. Sketch a best fit line through the data points by drawing a single continuous straight line through the points. Sketch the best fit line as close as possible to all the points and as many points above the line as below. That's how you draw a best fit line. Very, very rarely in physics have I seen where you are supposed to connect the dots, okay? Most of the time, especially when you have data that has been gathered experimentally, there's going to be some built-in error or flaws in your data, and your dots generally are not going to be perfect. Okay, you're not going to have like the perfect, these are where the lines definitely should be. Now, in this case, we didn't experimentally get these values. We essentially calculated them by adding 3 every second. So in our case, this line looks pretty straight and goes right through it. But that's just sort of because we're kind of doing this backwards. However, let's do this. So we're going to plot this. 1 second, 3. At 2 seconds, she's at 6, and so on. And so you've done this bit many, many times. Essentially, these are your x, y values up here in part A, and you're just going to plot this point. Plot these points to make the graph. Okay. One little nitpick I have here is I would say, well, let's not call it, you could call it position versus time. If I would put some kind of title up here is what I'm trying to get at. So T4 Angela. Okay, now you definitely want to write a little bit more neat than me, but you should always include some sort of a title. Okay, part C, quantitative analysis. Let me go back. Okay, we're good. Calculate the slope of the line you drew in part B by choosing 2 points on the line. Okay, that kind of goes back to what I was saying earlier. Your line should represent all the average, the average value of all your data. If you've got experimental data, your dots might not be perfectly on the line because they are flawed. They have error due to the whatever collection, error data collection you had. So you use the line to get your slope. Don't use your data, your flawed data, okay? Your line is sort of like taking the average of all those. I'm kind of using that term slightly loosely, but it's more powerful that way. So use the line and then fill in the equation below. So choose 2 locations on the line, not your dots. So on the line to calculate slope. Circle these 2 places on the line. Remember, do not use data points from the table. Very tempting, especially since these data points kind of are perfect. But you can see up here, for the answers for this example, we chose 2 points on our line. All right. We didn't make it very easy on ourselves, but we did. And so these are the points that we chose. You could have chosen any other points if you wanted to. Honestly, I probably, if I was doing this all by myself, I would have chosen the 0, 0 because it does seem to go through the origin. That makes your life easier. I'd say whenever you can, use the origin. It just makes things go way easier for you. One thing I want to point out is you should always show how you got the slope. Always show how you got the slope. All right. Do the equation. If you're given a space for it, show it on your paper. Okay. Don't just like put the answer down and assume that everybody knows you plugged the numbers into your calculator. Show the work. Okay. Especially on an FRQ, people are looking for that. The graders are looking for the fact that you know what you're doing. Okay. You didn't just accidentally pick the right answer. So show your work. All right. Now, the cool thing here is you might not have realized this, but when you take the rise over run, okay, the change in y over the change in x, the units stick around. So the units for y is meters. The units for x is seconds. And that meters per second is velocity, right? So check the units. That is a super powerful skill to kind of get used to doing, is start to notice when you start to compare values and you find the relationship between 2 variables in a graph or whatever. When you find the slope, the value of the slope tells you something about the object. Really cool. Okay, so then use the slope-intercept form of the line equation, y equals mx plus b. Write the equation. This is very important, okay? Y equals mx plus b is great, but the y-axis is the position, x. It's a little confusing. It's a little confusing sometimes because, wait, the x isn't the x value? No. That's position, okay? Pardon my terrible writing, but that's position, not the x-axis, right? So the position, remember what I said earlier, is get used to actually saying what these letters stand for. So position, or x, is 3 meters per second times time in seconds plus 0, because it intercepted at 0. Okay, a more general equation using standard physics symbols such as x, v, and t. So the letter x is, again, position, the letter v for velocity, and the letter t all by itself. You don't need to include units because it's a variable. You might choose different units besides seconds for time. Very good.